Yeah, hi. Hi, everyone. Good evening for those that are in Nigeria, and then good day for those that are in any other part of the world. Welcome to today's session. This is week two. If you can see me, kindly drop a comment so I can know that people are here live with us. I'm looking at the charts to know. Oh, yeah, Kinsley Zikora, I can see you. Who else is here? Can see about 10, 15 people on the live. So if you know anyone that's supposed to be here, please kindly let them know that we've started and they should join. This is week two. This is module two. Um, and we have Amarachi here again. She'll be talking about a lot of interesting things this week. Today, oh hi, Cyrus, you're welcome. Today we'll be talking about cryptography and consensus mechanism, and this is like a very interesting topic. I can't wait to hear all the interesting things that our guests is going to give us today. Okay, guys, I'm waiting for more people to join the live, so invite more people. Go to the group, make noise, let them know that we've started. I see you, Oxblix. I see you, Adeleke Simon. You're welcome to the stream. Thank you, everyone. Please remind those that tell them, let them know that we are here. They should come. They should know. Disturb them. Go to the group. And then also, if you are here, please, it's better when you oh yeah, Okorowa Obehi, you're welcome. Make sure to like this video and subscribe to this YouTube channel, because if you subscribe to this YouTube channel, let's say you forget next week's session, what's going to happen is that you are going to be able to see it once we go live. So once we go live, you get the notification, right? So please, if you can, like this video, but then make sure that you subscribe to the channel. It's going to help you a lot. All right. Okay, I can see that one people have joined. So today we are going to discuss about cryptography and consensus mechanism, and then Amarachi is here. She was here last week. I know a lot of you enjoyed last week's session. And then if you enjoyed last week's session, can you type yay in the comment section? So let's do yay or nay. So if you enjoyed last week's session, you can just help us type yay in the comment section, so we can be able to see those that enjoyed last week's session. Right. So thank you very much, everyone. Nobody enjoyed last week. Okay. So Amarachi is coming on stage. She's already here. We are bringing her on stage. Ukeme is also here with us backstage, and then we can't wait to get started. So Amarachi will be coming on stage just now. Okay, I can see a lot of you now. Thank you. Yeah.
Hi, Precious. Can you hear
So
me?
Amarachi will be coming on stage. I don't know why we have. Oh, I can see that a lot of you are excited about today's session. Thank you, thank you, thank you. I can see Kingsley. I can see Pop Pursues. I can see you. Yeah, you're welcome.
Hi everyone. Hi Amarachi.
Hi, can you hear me?
Yeah, I can hear you loud and clear. So, should I bring up your slides? Are you ready?
Yeah, you can.
Okay. All right. So I'll go backstage and bring up your. Amarachi, the floor is yours.
All right. Good evening, everyone. I hope you're all doing great because I am. So today we are going to be talking about cryptography and consensus mechanisms. And I believe I have a returning audience, or I also believe we have new visitors. So I'm just going to do like a quick introduction about who I am. So basically, my name is Amarachi Ugwu, and I am a blockchain engineer and educator. I'm also a co-founder of DigitSpay. You can check us out at digitspay.finance. And in my free time, I basically contribute to open source, and I am also a Mind Makers ambassador, just driving the change for more women in tech. So that's basically a brief intro of me. So I think Precious, you guys are going to be running and following me this slide. So because I already did my profile and you're still on this other one. So you can go to the next one. Yeah, the very next one. Okay, so we won't just jump to talking about cryptography and consensus mechanism. We are going to start from a ground level and build it up. So one very crucial part of this whole topic today is hash functions, and it's very important that you understand how this function works because you can find it literally everywhere. So basically, hash functions they are called a one-way function, and why are they one way? So it simply means that when you use this function and hash something, you'll get a fixed size hash once you've hashed a particular input. It can be data, it can be files, it can be anything. But you're sure that once you've hashed it, you're getting a fixed size output, which is called a hash. So the instance I gave you is SHA-256. So from the name, you can tell that once you use this hash function on a particular input, you're going to get a 256-bit output, which is called hash. So I believe you all know like a basic byte to bit to byte conversion. So it simply means that there are eight bits take one byte, and then if you do 256 divided by 8, you're going to be getting like 32. So most times, when you see an output that was hashed by SHA-256, you're most likely going to be getting a 32 characters, right? So when you hash like a huge amount of input, you're most likely going to be getting 32 characters output, right? So that is why we call it a one-way function, right? And another thing about this one-way function is that once you hash something, it is like it's like computationally impossible for you to get the input from the output, right? So let's say you hashed the name of everybody in this call together, and then you're getting just a 32, a 256-bit character out, right? So you're not able to get each and every one of our names from that hash. So that's why it's called one-way function. So when you just hash it one way, you cannot hash it either and two ways, front and back. That's why it's called one way. So another characteristic of a very good hash function is diffusion. So what this means is that when you change, like, let's say, even a single character in the input, the output that you're going to get is going to be significantly changed. Like, let me say I hash Amarachi Ugwu, and then I get 256 bits out, right? Or let me say 32 characters out. And then I remove the I at the end of my name. And then I have Amarach, I don't know what to call it, but you get the point. Something Ugu. Then I hash that. When you check the two hash that I'm going to get my output, they're going to be significantly different. So a good hash function is meant to be diffused, right? In the sense that when you change just a slight something, it significantly affects the output. So another good characteristics of a good hash function is determinism, in the sense that if I hash Amarachi Ugwu now, if I come back tomorrow and hash it again, it will still give me the same exact hash. So I'm sure that whenever I hash a particular set of inputs, I'm sure that it's going to give me the same thing over and over again, unless something changes. But once the input remains the same, it keeps giving me the same output. So another characteristic of a hash function is collision resistant. So it's like computationally impossible for me to hash Amarachuku and hash Okeme and get the same hash. Like it is a good hash function is meant to be computationally impossible for me to hash two different inputs and get the same output or the same hash. So hacking again is it should be non-predictable in the sense that I shouldn't be able to predict the input from the output. So a good hash function should be able to hash an input so well that they are totally like there's nothing in common. So I can't tell that it was Amarachuku that was hashed that gave me this 32 byte character, right? So that's one of the key features of a good hash function. So you can find hash function in use in something like password verification. So even in your Web 2 programming, you find out that you get to a point where I know like years back when programming wasn't like so secure like it is now. You find out that people like save people's password the same way. Let me say I use my password as Amarachi. You see that people save Amarachi in the database, right? But when hash functions came around, there are several hash functions, not just SHA-256. It's just that most computations, most hashing that is done in the blockchain use this hash. But the other MD5, you guys know them. So when hash functions started getting used, you can see that what people now do is when you give them when you're logging in or when you're registering and you're like you're registering with your name, your email, and then a password. What they do is that they take that your password and they hash it, and what they save is that hash. So the reason why this is secure is that even the person that saves the hash doesn't have the ability to tell what your password is because it is a hash function and it is one way. So when this your hash is saved, what you would normally do is when user comes to log in, they put in their email or whatever and their password. Then your programming, your in your program, you're like going to hash whatever they give you, and then you now do a comparison. If they match, then you go ahead and log the user in. So that is somewhere you see hash functions used very well. So another place that is used is in signature generation and verification. So I'll like leave this one because I have a section where I'm going to talk about it like elaborately. So, but when I explain it, you can see the role that hash function play in that. So next slide. Okay, so in this slide, we are going to be talking about Merkle 3. So Merkle 3 is like considered the data structure of the blockchain, right? Although you can actually have a blockchain without necessarily using Merkle 3, but then there are reasons why most blockchain use Merkle 3 as their data structure. And we are going to get into that. But before I do that, I want to explain what this diagram is really showing. So this diagram is just showing like what is going on in a block, right? Remember I told you that block is like the single unit of a blockchain, right? So and I remember I told you that blockchain, the reason why we have a blockchain is because we have blocks that are linked to each other, that are always continuing. Once a block is full, it is set aside. And when another one is full, it is linked to the previously full one. So this is like what is going on in a block. So, and in a block, there's something called a block header. So, see it like the metadata of a block. It's more like carrying the summary of what is going on in the block. So, you can see that inside this block header, there is a previous hash, there is a nonce, and there's a root hash. So, this previous hash is, remember I said that a block, current block needs to be linked to the previous block. So, this previous hash is what is holding the data of the previous block, right? So it is used to basically ensure continuity of the linking, right? So it's just like getting the block hash, the hash of the previous block, and then hashing it and then putting it in the block header of the current one, and that is how it continues. That is how it continues. So a nonce, so this is just a nonce in a proof of work setup, you won't see a nonce. But in a Bitcoin setup, that's a Bitcoin blockchain setup, you see a nonce. So I won't really go into that now. But then what I'm more interested is in the root hash. So if you look at this root hash, there is a lot of things linking to it. So root hash is just basically, it's more like a hash of all the transactions that are put in a block. Remember that last week I told you that see a block like a carton of biscuits, and inside this carton of biscuits, you lay down biscuits, you lay down biscuits until it is full, right? So see these biscuits now as transactions. And from our image, you can see that I have transaction 100, transaction 101, transaction 102, and all of that. So inside a transaction, there are things that are in a transaction. So you can find things like, so basically, a transaction in a blockchain is basically anything that alters the state of the blockchain is a transaction. So let's take, for instance, a transaction where I am sending, okay, let me say 1 Ethereum, right? It's a transaction. And in a conventional transaction, you'll find some things. You'll find the from, where the transaction is coming from. You find the to, where the transaction is going to. There are a couple of things in the transaction. So I think I'll save this for a later explanation. But just know that we have transactions um, in the lower level of these three. And then for us to get it to the root hash, we have to do some things, right? So you can see that transaction 100 is hashed to, it now becomes hash 100. So when I perform hashing on transaction 100, let's say I use SHA-256 to perform this hashing, I get hash 100. I do the same thing for all my transactions from 100 to 103. You can see that they've moved up to hash 100, hash 101, hash 102, and hash 103. So the way hash function works is that you just keep hashing and hashing and hashing until you have a single hash, right, which is the root hash. So in this diagram now, what we basically have here is a binary Merkle tree. The reason being that we are dealing with just two transactions at a time, right? We are just combining two transactions at a time, right? So what is happening here is that I hash a transaction, then I get the hash, right? Then I combine the two hash and I hash it again. So this is just like a very basic Merkle tree, but like a large blockchain like Ethereum, you could imagine the amount of hash that happens, right? The tree is a lot more larger, and then what just happens is that two transactions are hashed, then they are combined, they are hashed again, they are combined, they are hashed again until we have just one root hash, which is what we now put in our block header, right? So remember I said that you can actually have a blockchain without using Merkle 3, but then the reason why we're using Merkle 3 is because of we need something called Merkle proof. So, and this Merkle proof is just a way of simplifying payments verification. So you could imagine that in a transaction, like in a block, we can have like 500 transactions, right? And then you're a payment platform, and then you're connected to a client. And for that client to verify that a particular transaction is in a particular block, then you have to go through 500 transactions. That's cumbersome, you get? So that's cumbersome. So the reason why we use something like Merkle Proof is because we want to be able to verify that a transaction happened or is in a particular block without having to go through all the transactions in that particular block, right? So this Merkle proof, what makes up a Merkle proof? A Merkle proof is like you need a chunk. A chunk is basically what you're looking for in a particular block, right? So you also need the root hash, which is like the hash of all the transactions in a particular block, right? And then you also need what is called a chain. So this chain is just basically it's just basically the hash from the chunk you're looking for to the root hash. So from our diagram now, so if I'm looking for transaction, if I'm looking for if I'm looking to confirm that transaction 101 is in this particular block, right? So what I just need as my chain is hash 101, hash 100 to 101, and then root hash. So imagine that I just have to just skip through all the hashes that hash what transaction 101 happen like is in. So now if you look at this three, you have transaction 101 graduated to hash 101, and in turn it's graduated to hash 100 to 101, then you got to the root hash. But if you have like a broader Merkle tree, it's going to be like more chain, but it's not going to be as much as the total number of transactions in that particular block. So that is why we use Merkle 3, because it makes payment verification very easy. And for me to confirm that a particular transaction is in this block, just imagine if I have to go through 500 transactions for me to just confirm that a particular transaction is in a particular block. And then on the application level, the user is just going to be waiting and waiting and waiting and waiting, which will yield to like a lot of waiting and good and a very bad UX. So that is basically it about Merkle trees. One thing to take out is the data structure of the blockchain, and then we need the Merkle proof for us to perform a simple payment verification. So let's go to the next slide. All right, so this one is very interesting. We have the public key cryptography, or you can also call it asymmetric key cryptography, right? So the reason for the asymmetric is because you're going to be dealing with two keys all the time, right? So it consists of what we call a public key and a private key. So as the name says, public key is something that can be um, out in the public that you can share with somebody, right? But then your private key is always meant to be private, because you're going to understand why it's meant to always be private, right? So the public key can be shown to anyone, but the private, you need to keep it private. So um, it's computationally impossible for you to, infeasible for you to get the private key from the public key, but you can get the public key from the private key, right? So we can see the application of this public and private key cryptography in digital signatures. So I'm still going to save this digital signature explanation for I think the next slide or so. Then, but you can also see it play out in encryption. So let's dive deeper with encryption for you to understand how it works. So the way encryption works is that you want to send a message to somebody. You want to send, let's say, a message to somebody basically, and then you want them to only be the one to have access to it when it gets to them. So see it as a see it like there is a pathway on air, right? Everybody's sending their own transactions. See, like everybody's sending their own messages. But okay, we all use WhatsApp. You see things like this message is end to end encrypted or something like that. Yeah, because WhatsApp is a big platform. A lot of persons are sending messages. So when encryption is not possible, it means like I can just go in and read somebody's message, right? But then since everything is end to end encrypted, then I can only see the messages that I'm meant to see, right? So if encryption is possible, then there's a need for decryption, right? So this is where public key and private key comes in. So the public key is used to encrypt a particular message, and then the private key is used to decrypt it. So when I want to send someone a message, I encrypt it with my public key, and then when it gets to that person, they can decrypt it with their private key. So that is where you can find this public key and private key cryptography um, working work in action. So I think I'm going to go to the next slide. I hope that is where I'm meant to explain digital signatures. Okay, not that one. You're way ahead. Okay, yeah. Go forward again. Yeah. So so we have digital signatures, right? So basically, digital signatures use public key cryptography to provide message authentication, integrity, and non-repudiation. So the reason why we even have something like digital signature is okay. Think for instance that you have a client in the US and then you need to sign a contract and then you have to go all the way to the US or you have to wait for a mail or a courier to send the document to you and then you're able to send it, sign it and send it back. So things like this still happen, but then there is also room for other adoption like digital signature, where you're able to like sign a copy, sign a document, sign a contract digitally. And this is possible because of public key cryptography, right? So it is used for message authentication and for integrity, for you to be sure that, yeah, if it's this person that signed this, and if I can verify that if this person is able to sign this, then I'm sure that this person did this. So there is also something called non-repudiation, right? So remember that I told you that you need to keep your private key private. The reason is that when your private key signs a message or when your private key authorizes an action, you cannot come back and say, it's not me, or I don't know who signed it. The reason why it's private is that it's meant for only you. And when any action is performed by, is authorized by this private key, then it is you that performed it. So the blockchain can prove that this is the address this is the address that is linked to whoever that signed this message. So that is where non-repudiation is comes in. So you cannot something cannot be signed by a private key, and then you say that I don't know what happened, I don't know who signed it. So that is why one reason why your private key is to be private. The other reason is because of maybe when you make your private key open, you can have stolen funds. People can sign messages with your private key, so and you cannot say it's not you. Okay. So another thing again is there's also something we call the zero knowledge proof, right? So zero knowledge proof is a no-brainer because your is like zero knowledge. It's just you trying to explain or prove something without knowing without having any extra information about whatever you're trying to prove, right? So you want to be able to prove that something is true without you necessarily having detailed information about that thing. So it's just like me saying, I have 200 followers, I have 3,000 followers on just 3,000 followers on LinkedIn without disclosing what my LinkedIn name is or what my Twitter name is, or without disclosing any extra thing that will make the person to probably go to LinkedIn and start searching for me, right? It's just meant to be like, yeah, you just give somebody something and they have to prove it even without having extra information. So I think this is the point where there's a resource that a video that really explains this. I would have really demonstrated it, but since this is a virtual call, it'll be harder for me to demonstrate it. But that video really explains what zero knowledge proof all about. So, Precious, I think you can pull it up now.
So everyone see what I've got here?
All right.
All right, Zuko, turn her on.
Okay, so I can't see the bits. Now, are those two bits the same as each other, or are they different from each other, Jesse?
They're different.
I don't believe you. I think you actually picked two zeros, and you're like making a fool of me in front of everyone. So why don't you just show me the bits, and then I'll know that you're telling the truth.
Can't do that.
All right, so how are you going to prove to me that they're different without giving me any information about the bits?
Well, I don't know.
Okay, I got an idea. Here's what we'll do. I'll hold on to them, but I won't look.
Okay.
Now, I'm going to put them behind my back, and then I'll either swap them or I won't. And if they're really different, you'll be able to tell. But if they're both zero, then I'm going to catch you in this lie. Ready? Okay.
Okay.
Did I swap them?
No.
All right, so I didn't swap them that time, but I think they're actually both zero, and you're just bluffing, right? So you just guessed. So hold on a second. Did I swap them that time?
Yes.
Okay, you got me twice in a row, but you could be bluffing, right? So let's do it 100 more times. Hold on a minute.
No.
All right, 97 more times. This is why we use computers for zero knowledge proofs, is it takes too long. All right, thanks. Now, hold on. let me finish the lesson we just learned is, after we've done it 100 times, I'm really convinced that they're different, right? Because if they were the same, he wouldn't have been able to do that. So that's a proof. It's been proven to me that these two bits are different from each other. But it's a zero knowledge proof because I have learned zero information about what's on here. No matter if we did it 1,000 times, I'm no closer to guessing whether this is a 0 or whether this is a 1. He never showed it to me, and I didn't learn any hints about what's on here. All I know is the one fact that he wanted to prove, which is that they're different. So that's a zero knowledge proof. Thanks, Jesse.
Thanks. I'll take my data.
That analogy is very explanatory. Okay, I hope I can be heard now. So basically, that explanation is very clear, right? You can see that the man didn't even see. You can see that the man didn't even see if it was 0 or 1. He just kept. So it's more like he has to go through these iterations. He has to go through a large number of iterations, and by these iterations, there is no way that if they are different or I keep swapping them, there's no way that if they were the same, you know that it's going to return as though it wasn't swapped. But since they are different, it's that through those iterations, he can tell that they are actually different, right? So that is basically it. He wasn't able to know if it was 0 or 1 or any other thing because it's meant to be zero knowledge proof, right? So yeah, I believe that was very explanatory. So let's go to the next slide. Okay, so now we have consensus mechanisms. So what is a consensus mechanism? Let's just pick the word consensus. Consensus is just basically a way to reach agreement, right? We need to reach an agreement on something. So because we have thousands of nodes in the blockchain, there is a dire need of agreement for us to agree. So just take for instance, even in your family, a family of 5, family of 6, and then there's something comes up, you can see that it becomes even very hard for you to reach an agreement. Not to talk of a blockchain that has millions and thousands and billions of nodes, right? How do all these nodes come to an agreement to agree that, yeah, this is the right way to follow, this is the right thing to do, this is the best action to take, right? That is why there is need for a way to agree, right? So there are a number of consensus mechanisms, but I just have like 4 here, and I'm just going to explain how the whole thing works. So we have proof of work, which is more like the grandfather of consensus mechanism because that is what was originally used for. That's what Bitcoin used, and that was also what was originally used for Ethereum version 1. Even though Ethereum now adopts POS, proof of stake, but that was the first consensus mechanism that I used in its version 1. So how does proof of work, how does it work? So when you come to a proof of work consensus mechanism, there are people we call miners, right? And these miners compete to be able to mine a block. And basically what they do is that, block is the a single unit of a blockchain. And for a blockchain to keep running, there is need for blocks to keep being mined once there is need for it. Once the current block is full, then there is a need for to mine another one. So in proof of work, the way it works is that there are miners in the mechanism in the system where there is something called a block difficulty, right? So this block difficulty is just basically something that is used to measure the level of difficulty, a measure of the level of difficulty that is required to be able to mine a block. So it's more like an hash. So what these miners do is that they perform computations. They keep hashing the previous block, the data of the previous block until they're able to get a hash that is lower than the block difficulty. So when you hear like miners have to perform a complex mathematical calculation for them to be able to mine a block. So this is basically what they are doing. They are all competing to be the first to be able to get that hash that is lower than the block difficulty. And when they do that, they're able to broadcast it to the network, and whoever gets it first is rewarded, right? They are rewarded in ETH. So that is basically how proof of work works. And you have miners, and these are the same set of persons that approve your transaction, the same person that process your transaction in the Bitcoin blockchain. So, what is the pros of this consensus mechanism? There's high security. The reason why there's high security is because everybody have to prove, everybody have to work hard for them to be able to perform a process a transaction or even mine a block. So there's high security, and it is a lot more decentralized in the sense that there is no set of persons that is selected or elected at any point for them to be the ones that process or mine blocks, right? So it's decentralized in the sense that if you have the resources, if you have the money to be able to buy the computer systems, or if you have the computer power for you to be able to run and process all these calculations, then you can be a miner, right? So it's open to anybody. So it's not restricted to a set of persons. As long as you can afford it and you can run these complex calculations, you can be a miner. So there are a lot of miners, right? So it's not like a handful of miners, there are a lot of miners, which makes it even more decentralized. So, but the cons of this consensus mechanism is that you can see that from my explanation, it requires a lot of energy. It's energy intensive because if you're going to be running computer systems, keeping them always up, you're going to be using electricity, you're going to be burning gas, it's not carbon free, right? So there is high energy usage in this consensus mechanism. And it's also expensive because you're going to be consuming electricity, computer power. When your computer wears out, you have to replace them and all of that. So due to the fact that there is a lot of work to be done, and there's also a whole number, there's a lot of miners, it also leads to slow transaction. So these are basically the cons of this consensus mechanism when you're considering using it. So there's another one known as proof of stake. So this is what is currently used by the version of Ethereum that is up now. And also Solana uses it, even though Solana uses proof of history and also proof of stake. So how does proof of stake work? So in a proof of stake ecosystem, there are people called validators. And for you to be a validator, you have to have like a stake of the coin of that blockchain. So for you to be like a validator in Ethereum, you have to have an amount of Ethereum staked. The reason why you're staking this amount of Ethereum is because it just for to keep you sane, because you're more likely to lose or get your stake slashed if you do something fraudulent or if you try to perform an illicit action, right? On the blockchain, right? Or trying to validate or approve a transaction that that is fraudulent. So that's why you have to stake. So, but when you now stake, you're qualified to be a validator. So, but the way it works in proof of stake is that validators are selected as random. Let's say we have like 30 validators, right? So it's more like they are picked at random in the network to be able to process a block or even validate a transaction. Another thing again in proof of stake is that the chances of you being picked is basically based on the percentage of your stake. So it really means that if I stake 32 Ethereum and then someone else stakes 200 Ethereum, the chances that that person gets picked over me is higher, right? That person is more likely to be picked over me to be able to process a block or even validate a transaction. So that is the way proof of stake works. So one the pros of the proof of stake is that it is energy efficient because unlike proof of work where you have to perform complex calculations, where you have to use electricity and all of that. You don't do that in proof of stake. So that makes it energy efficient, and so it has faster transactions because there are a number of persons that are valid. Not everybody in the blockchain is a validator. There are a number of persons or number of validators in the ecosystem. So it becomes easier for transaction to be validated, right? It doesn't have to go through a lot of back and forth. So, and it's also more accessible. So one con of it is word centralization, because you know that the whole idea of having a blockchain is because we want it to be decentralized as much as possible, right? But in the case where we have like a number of validators, and we pick them at random, and then uh, the chances of them being selected is proportional to their stake, then you can see that it means that if I have like 30 validators, right, and then I have 5 out of that 30 have like really high stakes, and then the other 25 just have like the least required stake. So you can see that the chances that those 5 people are going to be picked more than the remaining 25, that the chances are higher. So it makes it even more centralized, where these guys get to validate more transactions than the other guys because of the difference in the staking. So it is more well centralized. So another consensus mechanism is the dedicated proof of stake, right? So it's more like, think of it this way: it's a proof of stake, but then it's more like a democratic version of it. So you know the way democracy works. We select a group of persons, and they were like saying, okay, we have two candidates for president. Then we have to vote for the person that we want. The person with the highest vote goes into power. You get. So in proof of dedicated proof of stake, we have delegates. We have people that are picked, a small group of delegates, and then the holders of the coin, of the blockchain coin, and now the person to like vote. Okay, we are voting for person A to be the validator. We are voting for him to be able to be the person to process a block or validate the transaction. So it's more like a democratic action have to happen for them to choose who they want to process or validate transactions for them. So basically, it has all the benefits of the proof of stake, and but the extra benefits that it have is that it's more scalable than proof of stake and proof of work, right? Because now we even have a smaller group of validators, so processing transaction don't have to go through a lot of persons. So it's just like a small group. So getting to agreement is faster. So that's why it's more scalable than proof of work and proof of stake. So even so now you can see that it is even less decentralized than the conventional POS, right? Because now we are still shrinking the number of persons that need to validate a transaction. So we are shrinking it, so it even leads to corruption. Because what happens when the people that are delegates start tipping the holders of the blockchain's coin? You can see that just the same thing that happens in normal democratic political world, the same thing can happen in this delegated proof of stake, because it's still the same concept of democracy that is applied. So it is still, there's risk of corruption to happen in this consensus mechanism than in proof of work or proof of stake. So another proof of consensus mechanism that we have is the Byzantine fault tolerant proof of consensus mechanism. So this whole this practical Byzantine fault tolerance consensus mechanism, it just came from the whole idea of the Byzantine fault tolerance, the Byzantine generals problem. So I don't know if you guys know about that problem, but it's more like the whole concept of it is there is a city, and we need like, there are 4 generals, and these 4 generals, they are staying at strategic places. They have camps in the 4 corners of the city. So, but these generals, before they take any action, they need to communicate. They need to communicate with each other to know if we are to attack, let's attack. If you are to retreat, let's retreat. So they want to be able to meet an agreement before they perform any action, such that they don't go performing an action where some generals retreat and some generals attack, right? So because when something like that happens, there's chaos. So
Sorry,
that's where this article by that.
sorry, Amarachi. Yeah, so let me just come in there for that Byzantine fault tolerance. So I'm going to assume that we have a lot of DevOps engineers here because it's it is when it comes to building a blockchain network itself, Byzantine fault tolerance is actually very important. It shows that okay, because I use this every single day. Do you understand? It determines the amount of nodes that should be in a network, right? There's a formula we use two f plus one, where f is default, the Byzantine fault tolerance, right? So it means if you have a set of 10 nodes or let's say 7 nodes in a network, right? And some because it's decentralized, you want high availability. If some nodes go down, what is going to happen? So you need to now put some fake, I won't call them fake nodes. They are the Byzantine nodes, which actually when the other nodes fail, the Byzantine nodes can actually, try and make sure there's liveliness on that network. Do you get? So that part of Byzantine fault tolerance is something as a node ops engineer, you need to actually take note of that and take note of the formula 2f plus 1. You can Google that, you know. Yeah. Yeah. So in terms of infrastructure, the infrastructure side of things, it is very important. Proof of work, proof of stake, and the others actually are it's also infrastructure, but with everything Amarachi has said, I'm just adding to what she has said. They actually work on more of like the validator side of things, in terms of like the software, how people stake, how they delegate, how should a transaction be actually how should the transaction be added to the blockchain. Do you understand? Sorry about that, Amarachi. I just had to come in there.
Yeah, no issues, no issues. All right, thank you for that, actually. So I just want to add in that the way the whole Pascal Byzantine for tolerant thing is. I just want to give like an analogy for you to like understand how this thing works. So let's say we have like a main general, right? And the client issues like a process a transaction request. So what this general does is that it has like a replica of other generals, which are like the persons that are handling the whole processing of transaction or in that particular blockchain. So what really happens is a client issues a request, and then this general orders that request. It's more like, think of it this way, like in if you watch all these general movies, before something has to happen, they have to like write an order, issue it to this district and all of that, those kind of things. So similar kind of thing happen where a request comes, then this general kind of like orders it saying, okay, I want this transaction to be processed. Right? Do you agree with it? Yes or no? He kind of like broadcast this order to the other replicas of the generals, right? So what these other generals on their own end does is that they issue their own, they verify that order. Either they are saying we want you to proceed or we don't want you to proceed. So let's say there are extra three generals, making them like four generals in total. And then like say the first general like okay says I want it to go on, and then he broadcasts it. So this the first general kind of like when a replica broadcasts his own response, the first general is like okay I have two yeses now. Then the other guy and he's broadcasting to everybody. So the other guy kind of like sends his own response. He has three yeses now. So one thing with just like what Jukeme said, we want to be able to handle, even if when a particular general is unavailable, we want to get enough response for us to proceed. So in PBFT, you need like 2/3 of the generals to be able to agree, right, to something to proceed or to verify that something to proceed. So once they've gotten like two out of the three, let's say the fraction of 2/3 of the whole generals that are meant to like issue a verification. Once it gets up to 2/3, then we can go ahead with go ahead with processing the order. So this is just basically like an analogy to back up what Ukeme already said. So I think this is the last slide, and then I think we should be able to start taking questions now. Are there any questions?
Yeah, yeah. Precious, are you there? Precious, are you
Okay,
there?
can you hear me?
Yeah. Before the
Yeah.
questions, please just give me a minute. I want to still explain something about that Byzantine fault tolerance because of the nature of what we are doing. So let me just quickly share my screen. The point is for us to actually have understanding. Um, if you can see my screen, Precious, let me know.
I can.
Okay, yeah. So Byzantine fault tolerance, right, in node ops determines the amount of nodes that should be in a network. As a node op engineer, your job sometimes can be, oh, I need to create a DevNet node. It should run this binary. Let it have social amount of RPCs. It should be able to do this. But how should you know the amount of nodes that should be in a network? Because you can't just say, okay, let me just create 20 nodes, let me just create 50 nodes. There has to be a balance, and in that balance, the Byzantine fault tolerance is actually what determines, using this formula tells you the amount. So it says refers to the minimum number of nodes required for tolerance in case there is any fault, in case some validators or some nodes goes down, would your blockchain network go down also? If it goes down, then it's not really blockchain anymore. Do you understand? You understand? So, and ensures the system can reach consensus even if some nodes act maliciously or incorrectly. So, maliciously meaning if there are some bad actors there, or if there some I mean, these nodes are just servers, to be honest. Imagine you have a server in your house and NEPA takes lights, which doesn't really happen, right? And NEPA takes lights. This node will go out of sync. Do you understand? It's going to go out of sync. So if it goes out of sync, what's going to happen with the other nodes and what's going to happen to the network? Because of the amount of net nodes you've created for that network, there's going to be enough tolerance and almost no downtime, right? So if we look at this, the F actually means default in that formula. F represents the maximum number of nodes that can be faulty, or the Byzantine nodes is actually the F in the 2F. So it means if I want to create a blockchain network, I will now say, okay, I have four Byzantine nodes. So that's 2 times 4 plus 1, right? 2 times 4 plus 1 determines the amount of nodes that should be in that network. Do you understand? If it's a very small network, most times it's usually a network of 7 validators and 2 RPC nodes, right? So if you say 2 times 2, that's 4 plus 1, that's 5 plus your 2 RPC node, making it 7. Do you understand? So that's to tolerate F Byzantine nodes, the system needs to have at least 2 F plus 1 nodes, you get, or replicas. You need to have 2 F plus 1 replicas, right? So why do we have to do that? So this is because with 2 F plus 1 nodes, even if F nodes are faulty, that's the Byzantine nodes, the amount of Byzantine nodes are faulty, there will still be F plus 1 correct nodes to actually run that network. Do you get? So I just thought I should share this because this is something we actually use a lot anytime we are asked to, deploy or create a blockchain network.
Thank you very much for
All
that
right, thank you
vivid.
very much. Okay, I think okay, well, Kingsley Zikora is asking if they can have the notes that you are creating. I think that should be the slide you shared.
Okay. Yeah, I think the slide is already with. You can share with the comments.
Yeah, we share that.
Okay, okay, you share. Okay, so I think that we have some questions in the, yeah. So if you guys, if you have question, please kindly drop it in the chat. You guys know how we do it. Drop it in the chat. I'm going to project it on the screen for Amarachi, and then she's going to answer them. All right. So there's a question here. It says, "Is hash related asymmetric encryption?" I don't think I understand this.
Okay, I
Amarachi,
guess
can you
it's
see the
saying,
question?
yeah, I can see the screen. I
Okay.
guess it's saying asymmetric cryptography. If I'm wrong, then you can.
Yeah, I think he's asking if it is like asymmetric, that's like a two-way encryption thing. But then hashes, I mean, if you are doing any form of like cryptography, there needs to be an hash. Any
Yeah,
kind of cryptography has an hash. So the question
yeah.
doesn't really, it doesn't really question itself, if I would say that.
So basically, if he's coming from the point of encrypting and decrypting, for you to
Mm,
encrypt hash, so there's hash there.
mm,
You
yeah.
get, even if it is asymmetric cryptography you're doing, even if it's digital signature you're trying to generate, you need to
Mm,
have there's an hash need to be performed, right? So I guess that's the relation he's asking about.
mm,
Can seed phrase be said to be public keys? No. Seed phrase is mnemonic, right? So there is seed phrase, there is public key, and there is private key, right? So if you see a conventional public key, it's a lot more longer than, let's say, your Ethereum address, right? But it's still you get your address from the public key, right? Seed phrase is like a set of words that is used for hierarchical deterministic wallet. So what is a hierarchical deterministic wallet? You know, when you open your MetaMask, you can create account one, account two, account three, even account 20. So that is possible with an account that was created using a seed phrase. So it gives room for there to be like a hierarchy of accounts, right? But then you can still go ahead to just generate a public and private key just once for yourself. You can do that. So, but when you want to have a hierarchical deterministic wallet, just use seed phrase. And that's why they tell you keep your seed phrase safe, keep your private key safe, because private key is just linked to a particular address, is asymmetric to just a particular public key, right? So, but when you want to have an account that has a wallet that has multiple accounts in it, then you need to use seed phrase, right? So, but then public private key cryptography can seed phrase be?
Yeah, so let me support Amarachi there. Amarachi has said it all, but I'm going to explain it in a Web 2 or DevOps manner, right? Just Amarachi explained the blockchain side of things, but Web 2 and DevOps. Public keys, you know what it is. As SSH, if you want to SSH into any machine, you have to create a key, right? And when you do SSH key gen, it's going to create two keys for you. It's going to create a public key and a private key. The private key is what you use to SSH into the machine. The public key is what you can now use to give access. So if a guy now, I create an EC2 instance on AWS, right? And I want that guy to have access to that machine. The guy can create a private key and a public key, and it will send me the public keys. The public key I can now announce to the whole world or put on AWS, and anybody can see it, right? He on his own and has the private key to have access to that machine. That's in like the Web 2 or DevOps side. But what Amarachi said now is saying it in terms of the deeper part of it, in terms of Web 3. Anytime you create a wallet, right, it's going to ask you for a seed phrase. The seed phrase in Web 2 terms is actually your password in a sense, right? And you should not share your password. I'm also going to say it here. Don't share your seed phrase. Don't share it. People can use it to hack your account. I noticed that in the last session, somebody commented. In fact, I saw three comments talking about they have money in OXX wallet, and they actually put how can they send their money to Binance, and they share their seed phrase on YouTube. Like, don't do that, right? It's your password. Okay, thank you.
I also want to add, most times when people do that on comments, I create YouTube videos, so I get a lot of that. So most times they're actually scammers. You
Are you
get?
serious?
I'm telling you the honest truth.
I saw three of it. I'm like, okay,
I'm
okay.
telling you the honest truth. So their
Mhm.
targets are actually greedy people. So you see
Mm.
persons that will copy that those seed phrase and go and import it. So there's something they do. They'll kind of they'll kind of like have a particular token inside that they see. When you open it, you see that there is money, but then there's no what's it called? There's no gas fee for you to bring out the money. So
So you have to
what
fund the wallet.
what I now want you to do is to put some gas fee, but that particular wallet is already coded in such a way that when you put that gas fee is moved immediately. You get? So there might be like 1,000 persons trying to send in gas fee into that particular wallet, and as it's entering, it is leaving. So they can use that to like really
Yeah,
rake a whole lot of money.
I did
So
see
most
it
times
that
when you
way.
see people doing that, on your,
Mm.
your comment section, they're actually scammers, like 90% of the time.
Thank you for that. Like, thank you so much because I like that's actually a very brilliant way to scam people. Do you
Exactly.
get like reverse psychology or something? Okay.
That's actually a very interesting one. Very, very interesting. Wow. But
Okay.
like, e-
Are there more
like
questions?
Nigerian prince,
Exactly.
Nigerian
And
prince on Thursday.
and they actually come to any session that they see that you're handling newbies because they are most likely the persons to work on. You get?
So we
Oh,
should be deleting those comments because
Yeah, yeah,
yeah.
mm,
you should.
All right. So thank you very much. I'm not seeing any other comments. Kingsley, thank you very much for being very active. Maybe we should give you some extra points because you've been very
Thank you.
active today and you stayed from beginning
we'll
to
give
the
you
end.
prize, Kingsley. Don't worry. Well, on it,
Yeah,
you get a prize. Just be consistent.
you will get a prize. You've been very, very active today and very, very consistent. All right. You everywhere on the charts. Okay. I can't see any other question here. Can't see any other question. That means Amarachi did well. I mean, Kingsley already said that. The session was well explained. Thank you, Amarachi.
Thank you.
Amarachi is an excellent teacher, though. So, yeah, thank you very much.
Thank
Um, okay. Thank you, everyone that came on for today's session. Um, see you next week. The task for this session is already on the sheet.
I think
Okay, there's a question. What is proof of history? Okay, there's the first question is what do you mean by stakes on POS?
Okay.
I hope you guys are not asking this question so that you win something. So ask this question.
All right. So I think I'll take the first one. Which says what do you mean by stakes in POS? Okay. So you already know POS is proof of stake. So stakes is you're staking something, you're giving something up for you to be a validator. And most times, in the case of Ethereum, what you're staking is Ethereum. I remember the time we were doing that stake, you're going to, I think it was about 32 Ethereum, the minimum you can stake for you to be a validator. You have to stake this amount of Ethereum for you to be able to be chosen at random for you to validate or process a block. So I think that answers your
yeah,
question.
yeah, it's like you're investing. Do you understand? If you the point is we need people, you guys to use all these things, Binance, all those things. When you're staking, you're putting some money, it's like you're investing money and locking it somewhere. Do you understand? To get some like profit. But in this case, proof of stake, like she said, in terms of consensus mechanism, is like you're investing in that chain using their it's usually the native currency of that chain. Like I work in Supra now. For the validators that are there, they stake Supra to participate as validators in the network. So it is for Ethereum and some other proof of stake consensus mechanism blockchains.
All right. The next question is what is proof of history? Okay, proof of history, you find this consensus mechanism in Solana. So Solana basically is like a hybrid. It uses proof of stake and also uses proof of history. So why it uses proof of history is, the way proof of stake work is that there has to be a consensus about a particular transaction before it gets processed. But the way proof of history works is that as the request is coming in, it's kind of like ordering it. Like, let's say a request came in by 6:10, another one came in by 6:11. So it pre-orders it, because the way most of the blockchain works is that once a particular, you can have a number of transactions, but it depends on the one that the validator picks, gets to be processed first. But then in proof of history, there's already like an order even before consensus. So that's why you can see that Solana like can process more transactions than Ethereum in a second. I think Solana does like 250, 2,500 to like 65,000 in a second within this range. But like Ethereum does like 30 to 100 within a second. So because of the adoption there, because of the proof of history that Solana uses, is able to process more transactions. So it's just basically used to order requests even before consensus. Is that it?
Okay, I think
Thank
there's a
you.
question on where do I get 2032 ETH? It sounds like a joke, but I'm going to talk about it. You can actually get, let's put that question up. You can get 32 ETH for testnet, right? Right, using a faucet with
I was
consistent.
also interested in that answer.
And also, there's something very interesting that we've been working on internally. There are different things called DVTs. DVTs are distributed validator technologies. There are some companies like Obo, I think, which other one? Obo, there's one other popular one like that, but I know I've used Obo to stake, like distributed validator technology in terms of you have a lot of people are contributing to stake 32x. Do you understand? So in the whole contribution, you now in that pool, you can your own contribution can be 0.02, and you have some senior men who are contributing the highest you get. But all of you have different nodes running, but the validation part of it is a distributed technology.
Yeah, it's more like there's a way they call it. I've forgotten, but I think it's leased, more like leasing. So it's more like you don't have up to 32, but you can come together in a pool, then get up to 32, and then one person serves as the okay. You've shared the link. So yeah, I think that does it. Okay, do we have any more questions?
I think there is okay.
Someone asked a question for assignment. Can I just use Python to do hashing, then explain the steps?
Yeah, I think so. You can use anything now. It's just we're talking about just hashing now. You can even use, like I said, SSH key. Do you understand? Public private keys. Do you get? You can use the steps Amarachi has explained in terms if you want to go really deep. Zero knowledge proof. Can they use that Amarachi or something? Or
Oh,
what other steps did you talk about for hashing? Because that's the assignment.
okay.
The assignment implement a simple hashing function and demonstrate how it works.
Yeah, I think there's a lot of hashing now, even in your
Yeah,
Web2. There's SHA-256 for the blockchain. I know
yeah.
there's MD5.
MD5
Even
hash,
most programming languages you find hashes. The only thing is just them.
RSA.
Yeah, exactly. They work the same way. So if you anyone you're using and you can explain it, I think that works.
Yeah. Okay. Any other question here? Yup. Okay, there's no other question. I think we are good.
All right.
We are good. All right. So, guys, if you're not in the community, make sure you join the community. The form for submission will also be open. Let me talk about the last assignment. For those that did the last assignment, someone so I think I saw the comment this morning when I woke up that he did the assignment, but it was on his laptop. Please publish it. It's important that you publish this assignment because yes, it's true that you're learning these things and you are here gathering all this knowledge. People need to see that you're doing it. That is why we encourage you to publish these things. When you publish it, people see you. People see people see that you are doing this thing. People know that you are learning these things, and at least they can be able to understand your thinking, your course, your the idea. They know that you're understanding the things that you are learning from these sessions. So it's important that you publish it. So if you've not published the last assignment, you can use places like Hashnode, you can use dev.to, you can use LinkedIn, you can even publish on LinkedIn. There is Medium. Anywhere you publish is fine because you don't know who is watching, you don't know who's going to read the article and be like, oh yeah, I want to hire this guy because you understand this particular concept. So please, this is me encouraging you to make sure you publish your assignments and send it in using that form. That form will remain open until like maybe Wednesday, right? Then also for this week, please make sure you submit also for this week. It's important that you do that. Submit also for this week. All right. So we are going to tell you the procedure for submitting the assignments by Monday. So use the weekend, rest, enjoy, spend time with your family, and then next week you can get on with doing the assignments. And then on Saturday again, we are going to be here for week 3. I mean, this is 2/7, right? So I believe that we can all make it to 7/7. I believe you all that we can, you are going to stick with us to 7/7. This is 2/7. And then I believe that this has been an amazing one. Learning about blockchain the first time, and then today learning about cryptography, right? So make sure you show up next week. The event has already been added to your calendar. So just check. We are going to update the YouTube streaming link every week. And then once we update it, you're going to get notified that it has been updated. And then, yeah, and then you can be able to join. So see you guys next week. But before then, see you in the community on WhatsApp. Thank you very much, everyone, for coming. I really appreciate. Thank you very much, Amarachi. You've done an amazing work. Thank you very much. Yeah. All right. Thank you, guys. I think we're going to end the stream now. See you next week. Bye bye.
Bye.